is about the assignment that you need to prepare to fulfill the course requirement, and let me just walk you through the materials that's available for you to work on as you do your assignment. So you go to the link, you go into that link first, and I'm going to go through the information here. It says here that you should spend roughly 10 hours on this assignment, plus minus 5 hours. It says, important, go through the previous lessons on R and multivariate statistics before attempting this assignment, because you need the background information before you could effectively work on this assignment. And this assignment is for you to write a 3 to 6 page with figures data analysis report that describes the provided data in terms of descriptive statistics, distribution of the data, univariate analysis, correlation and regression analysis, and also multivariate statistical analysis. And the result should be in the form of a paper in the format of PDF. Given here, to help work on your report, another analysis that I did for a data set, and inside this zip file contains the code, the data, and also the report, the sample report on the data. I also provide here the report template. So let's click on this report template first and see what it is. I downloaded it, and let's see the contents. So it is a simple template where you have your running title. That could be a short title of your longer title, and then the title itself. So don't put it inside the square bracket. This is just to show that you need to replace the entire title here with your title, like that, and then also your name. Okay, the table here is auto-generated, so once you've added in your text in the middle here, and also where I put the your text part here, then you would increase the number of pages, and each part will go to the next page accordingly. And then if you want to update this table, you just right click on it and then just click on update field, just to make sure that it updates everything. Then you just click on update entire field to update it. So we did not change anything here, so that's why it wasn't updated. And if you created figures, then you can paste it above this figure caption here together with your figure caption. This is also, see, no, so it's not added to the table of contents, but it's still the format that you need to use for your figures are like this. And also your references list using the format of our school. You can use Mendeley or EndNote, just as long as the format is consistent and complete. Then you should be fine. So that's the report template. Let's go back to the assignment, and let's take a look at this CSI analysis folder. I downloaded it, and look at the contents of the folder. As you can see, there are the RStudio project file, and there's the data folder. Inside this data folder, we have the data that we worked on to create the report. Inside the docs folder, there's that sample report that I mentioned, and also the report template, similar file as before. Inside the figures folder, we have a sample figure, but it says here sample figure not for use. This is not to be added to your report, it's just a sample figure. This is where you would output your figures once you run your R analysis. And inside the R folder is the script. To open this project, you just double click on this CSI analysis R project file. It should open up, and if you click on files, you would see the folders that we saw in the other window with the data, and this is the script that you can modify to suit your needs for your own data. I'll just go through the code here. It says, important to students, please modify the code below so you can prepare your own unit report and plots. You write in your name and then the title of the course and the date. And then this line here is for you to import the data. So let me, to run it, you just click on this, run, and you see the data has been imported. Notice that the data is stored inside the data folder of that R project folder. And then please read the comments here because it gives you useful information on what the command does. So for this one, head_df means that we want to look at the top rows of the data frame. Click on that and you see the topmost, the first 6 rows of the data frame that we've imported. And this dim_df, if you run this, then you'd see the dimensions of the data frame. You can also see the dimensions here. And if you click on summary_df, then you see the summary of the data. This is basically the descriptive statistics of the data. It shows here for the column sample, we have 9 categories, 9 elements for cars, 5 elements for plant, and 6 elements for scene. And these are the concentrations for each of the columns, the descriptive statistics for each of the columns. For magnesium, the minimum is 3,750. The first quartile range is 3,905. The median is this, the mean is that, the quartile, the maximum is this. And that is the same for all the other elements in the data frame. Let's go back to the script. This sample names for the X label is just for you to recreate this column here, because you have this column samples inside df. If I click on that and you see the df, you see there's 9 elements for cars, like what I mentioned. And this is just to recreate that column. It's basically repeat car 9 times, then followed by a repetition of plant for 5 times and repetition for scene for 6 times, and put it inside this variable. And for this part here is to create the scatter plot. Now this might be something new, or maybe you've come across this inside the swirl lesson on graphics devices. You can plot like normal, and you get the plot here in the plot window, but for your report, it's best for you to export the plot into your desired resolution and size. So to do that, we use this JPEG function together with the dev_off. So this runs in a package. So here it creates this scatter_ca JPEG file and put it inside the figures folder. That's why we have these figures here. We have a resolution of 300 to make it as clear as clear as possible for your report. Well, not as possible, but suitably high resolution to look nice in your report. The dimensions of this plot is in cm, and the height is 8 cm by 8 cm, which means that it's a square plot. This is to set the margin. The margins of the plot from bottom, left, top, and right. So this is the bottom, this is the left margin, the top margin, and the right margin. So that means there's some space at the bottom, some space on the left, less space at the top, and even smaller space on the right. And this is the actual plot. So here we want to plot the calcium or the Ca column in the df data frame using a marker of style 19, which is a filled circle. This XAXT none means that N means that we disable the X-axis labels so that we can use our own labels. And the type of the plot is O. We'll see what it looks like later. The X label or the X-axis label is called location, and the Y label is called calcium unknown. And we color code the plot by the sample categories. And before we can use sample categories, we change it as S factor. This is where we plot the axis, means the axis number 1, which is the x-axis. Add from 1 until the number of rows of the DF. So there's 20 rows, so it's 1 till 20. And we label it according to samples. And we also add a legend. We put it in the top left. There's the car, plant, and scene. The marker for the car, plant, and scene is all the same marker, filled circles, and the color for the markers is black, red, and green. And every time you open up a JPEG graphics device, you always need to close it. So if you run this thing, this block of code, you have to run from the JPEG into the dev.off for it to be complete. That is important, or else you would find some curious errors if you just run one and then forgot to run the other. So if you run the JPEG function, you also should end it with a dev.off function to close it, to close the graphic device. So basically this is just to open the graphics device, and this is to close it. So if you open it and you never close it, so it would overwrite your existing plot inside that graphics device. Now if I run this, you would see it appear in this figures folder. You would see the scatter underscore CA figure appear here. So run it there, and then you can click on this to take a look at the plot. Now this is the same for the other plots, except for this line of code is just to prepare a box plot. Run, there you see the box plot. And then this is for the zinc scatter plot. And then a box plot for that. So that's the distribution and visualization of the data. Now to compare the means between groups, we can use ANOVA, similar to hypothesis testing, except for we don't do it for 2 samples, we do it for many samples or many categories of samples. So this is the ANOVA analysis. We only use the first and fifth column because we're just interested in, let's see, first one, all rows between. Okay, let's run this first. Oops. Let's run this first. Yes, we extract just the calcium column and also the first column. We put it inside this df AOV_CA, and then we run the analysis of variance using this function AOV on the sample. And you see here we look at the whether one of the sample here, one of the categories here are significantly higher than the rest or significantly lower than the rest for plant and scene. So I run it by this way, I get my result, and to see the results of the analysis, I just run this line. Here you can see that it is lower than p-value of 0.0001, means that the difference between plant, scene, and car, the different categories inside data frame, is significantly different. Between one of those are significantly different. And you can actually guess it once you look at the box plot. You see that one of them is definitely much higher than the other two, which means that the ANOVA, when you compare the means for all the 3 categories here, you see that at least one of them is different than the others. And then we run it for zinc and also for magnesium. Now we go to cluster analysis. This is just to create another data frame, but we remove the first column because C-1, because we cannot run cluster analysis on non-numeric values. If you look into df here, you see that this is non-numeric, so you can only work with the numeric values for HCA. So let me run this, run, and then recall that we need to only use the data in the form of a matrix for HCA in R. You run that, we change it to matrix, Then we name the rows of the df here using the sample. You can also read it here at the location of the plot. Okay, let's look at df temp first. Where is that? This is df temp, so this is row 1, 2, 3, 4, 5. And we want to name it according to car, plan, and scene. So I use this function here, run, and then now let's look. There, he has changed it to car, plan, and scene. And then we run hierarchical clustering analysis. But in the video before, we use this hclust function, but there's another function that we can use to create a cluster analysis together with the heat map. So in this example, we use that heat map function here instead of hclust, but you can explore using hclust too if you fancy a different way of running it aside from here. So let me run this. And now you see this created heat map CSI. There, the heat map is generated. Notice one thing interesting about this is that for this x-axis or this parallel to x-axis direction, you see the two groups have been created. It's not because of the variation between the elements, but it's more of the magnitudes of the elements. If you remember, potassium, phosphorus, and calcium has a much higher magnitude compared to the rest. And if you look at it from this side of the plot, you see that the magnitudes would separate them to different groups, but that is not really interesting. You want to look at the variation between it and not the actual magnitude. So this is one reason why we need to normalize the data before, or make them all the same, or transform them to normalize them so that you can run the hierarchical clustering to tease out, to extract the variation or patterns in the changes of the values instead of the actual magnitudes. So that's for cluster analysis, and this is using a different method just to compare. This is using the linkage method of complete, and this is using the average linkage method. And then this part here is for the principal component analysis. To use this, to use one of the function here, data ellipse, to draw the circles, you need to install this package first, car. So you might need to type install.packages for the package car in double quotes before you can load this package. So let me run this first. I've already installed it and it's loading it, works fine. And then run my principal component on the data, also works. And then I plot the figure from JPEG. Make sure I cover everything until dev off, and then run. And I see my biplot CSI figure, and it says that this car and scene has the same characteristics, so probably the samples come from the same location. The scene location comes from the car and not from the plant. So that's just a very quick look through the code that you can use to work on your report. This code is for the CSI analysis, but you can modify this for your own dataset to prepare your own report. Let's take a look at the report. It's inside the docs folder. Double click on the CSI sample report. And using the template, you just need to type in the text. You can write in a short introduction. Remember that the report is only from 3 to 6 pages, so I think you probably use the maximum number of pages because of the figures you need to add in. You write what's appropriate in the report, and this is for the CSI analysis report. So you notice that I put the plot in there, and then the heat map, the comparison between the two cluster analysis, and then the PCA biplot or scatter plot between principal component 1 and 2, and then a short conclusion and references. So this concludes a brief walkthrough of the CSI analysis report template and data analysis template for you to use on your own report. Good luck!